Hello, everyone. This is Spencer Snowling from Hatch, and I'm glad that you can join us today for what is the final GPSX monthly webinar for 2022. Today, we're going to be talking about using Monte Carlo sensitivity analysis for analyzing your wastewater treatment facility, both for design type parameters and for operational parameters as well. And I have my colleagues with me today, Nicholas Piccolo and Jacob Barkley, and they will be presenting various case studies that we have put together to illustrate how to use this probabilistic tool to analyze a wastewater treatment facility. So as per usual, when we do these webinars, if you have any questions, I encourage you to type them into the GoToWebinar questions box. In your little GoToWebinar dashboard, there should be a box there. You can pop that out and type your questions in, and we will see those as they come along. And then we will stick around at the end of the presentation today and answer as many of those as we can. Okay, so the plan for today is that we are going to be using, I'm going to talk about using Monte Carlo analysis for design and operational analysis of your layout. I will talk about the tools that we have available. So that will be either the built-in Monte Carlo tool that's part of the GPSX Analyzer feature, and also about how you can do that same kind of analysis using Python. And then we have two case studies. Nick is going to come in and do a steady state analysis while introducing some uncertainty into some of the parameters. And he will be doing that with the first tool that I mentioned. And then our second case study from Jacob will be using Python to drive a Monte Carlo style analysis, but it will be a dynamic run. So we're going to introduce the variability and the randomness into dynamic elements. And you'll see how that's going to be a different but sort of equivalent way of studying it. And they each have their own interesting aspects as well. So at the end of that, you'll have sort of seen how you can use this tool and sort of give you some thoughts about how you might want to apply that to your projects. So at the end, I'll have a few sort of concluding thoughts of where you can go with this tool, which I find to be really a fascinating one to use. And as I mentioned, we'll answer the questions at the end of the webinar. Okay, so on to using Monte Carlo for design and operational analysis. So if you've not heard of it before, Monte Carlo analysis is not one specific technique. It's actually a catch-all term for various types of sensitivity analysis methods. But they all sort of share the same idea. You run a large number of simulations, and what you do is on each one of those runs, you sample a bunch of different input distributions to create a set of inputs that you put into your model. Then you run the simulation, and then you can analyze all of the outputs that you get. So in this case, you are sort of ahead of time deciding what you think those input distributions are going to be. And then every iteration of the model, you will find a different value being used, and you do a different sample set. They're all sampled from independently from each other. And then you run a simulation, either that steady state or dynamic, and then you collect all of those outputs. The outputs now, instead of having just a single value like you would get when you do a normal steady state solution, instead of having a single value, say for your effluent ammonia, you are now going to have a whole set of values. And so you can plot the distribution of those values in a histogram and see sort of where that falls, in the scale of what you were trying to achieve. So it's more information than you'd get from a single deterministic run. So Monte Carlo is, to a certain degree, kind of considered a bit of a brute force method in the sense that it is just powered by very large numbers of simulations. So therefore, it requires a bit more time and computational power than simpler methods. But I don't think that's a negative thing. I like the idea that Monte Carlo takes advantage of the large number of simulations to be able to explore the space of performance of your facility. It's really useful for situations that have uncertain inputs, like say, for example, there's a parameter, a growth rate, or some, oxygen transfer efficiency, or something that is difficult to measure independently. You can use Monte Carlo to sort of introduce a bit of variability there. So that's good for that situation, and also systems that have, very complex internal interactions or boundary conditions. So if your system has some sort of element to it that you're really trying to excite to be able to understand what the limitation of it is. You might not catch it by a regular, normal, sort of one-dimensional sensitivity analysis just by stepping through a single value. So here you're going to be letting the big sort of cloud of simulations kind of cover all of the ranges of the inputs. And so hopefully you'll be able to capture and explore where that area is, where there's some interesting behavior in your model. And these can be employed, depending on how you set up the inputs and outputs, can be employed for, both what I would call design analysis, where you might introduce some variability in the loading and so on, and study the size of your plant, or operational analysis, like we're going to see in some of the examples today, where how much you're wasting, or chemical dosing, or, receiving septage deliveries, those things, those operational type things can be part of it. So, and almost all of these types of analyses, to me, are interesting to look at from the point of view, and I know this is what our clients are doing, is that looking at the effluent quality. What is the probability of compliance? So I ran 1,000 simulations, and I want to know what percentage of the time did I meet my effluent ammonia target. Okay, so just to really quickly summarize how this actually is happening when we do it, is first of all, we are going to pick several parameters, and we do these Monte Carlo analysis on all the parameters together at the same time. So we're going to pick here 3 of these. So let's say, for example, influent flow, and we are going to assign it, as it's showing here, a normally distributed set of values. So we'd specify the mean and standard deviation. We're going to do the same thing for a growth rate in the bioreactor, and then we're going to do the same thing for one of the settling parameters, say, for example. Now, these don't have to have the same distributions. You can use different shapes. You would obviously use different means and standard deviations and whatever. Those are all part of your decisions before you get started. So we'll do all of those, pass those numbers into the model, and then run a steady state simulation, for example, and get an output here. So this is predicting what the effluent would look like. Then we resample those, get new numbers, run the model again, and get a new output. And then we just keep doing that over and over and over again. So here I'm showing 4, but in reality, you would probably want to do many hundreds or many thousands of these types of simulations so that you can get a lot of spread of results and you can define the tails of your distributions quite well. So once that is done, you then take up all of that output, and then we look at those values. And for all of the things that you collected outputs on, you can now plot the probability, or you can plot the distribution of the answers. So for example, here, if I was looking at ammonia nitrogen, we can see that we got answers that were as low as 0.8 and as high as almost 9 milligrams per liter of ammonia nitrogen. And we can see that most of them fell here to the left, meaning that they were, down here around 1 or 2 milligrams per liter. And you can, for any value, calculate what is the percentage of the runs that fell either below or above some value. So here we're saying that it's 86.3% of our runs fell at 3 milligrams per liter or less for the effluent ammonia. And you can generate that for all of the things that you have output for. So this is where this kind of probability of compliance comes in. You're introducing some idea of randomness or uncertainty around some of the parameters. You can do that based off of historical data, or there's often places in the literature where you can get that kind of information. And then you're now saying, here's my results. It looks like most of the time I'm pretty good, but not all of the time. So you can get a sense of that value. So we have these 2 ways of doing it right now in GPSX. The first one is the built-in GPSX Monte Carlo analysis tool. And if you click on the Analyzer button, which is this one right here, you'll get this menu, and you can see you can select it from the bottom. You have to pick and choose which parameters that you want to use and what those details will be. And Nick will show you how that works in our first case study. And then you can use GPSX's graphing functionality to produce this graph here. This is actually covered in quite a bit of detail in tutorial 13. If you open up our GPSX tutorial manual, you can do it yourself, or you can actually come to our YouTube channel and take a look at the video there. The other methodology is to use Python. So as you may know, you can use Python, connect it to GPSX, and use it to sort of control and run simulations in GPSX. So in this case, Python would be generating the numbers that we are going to use as the input for our models, running the simulations, collecting that output, and then presenting it and doing some analysis of the results. So Jacob will be going through how to do this. Now, of course, this is using it sort of programmatically. So you have a, it's a very open method. You can do kind of almost anything that you want. And so we wanted to demonstrate some methodology today that will introduce randomness in a dynamic sense. So using Python, if you haven't tried that out before, is something that you can take a look at in tutorials 14 and 15. 14 sort of introduces the Python connection, and 15 shows actually a very simple sensitivity analysis. And then you could step it up from there into doing something more like Monte Carlo. Okay, so there's a few pros and cons of doing Monte Carlo analysis. One of them that I think is one of the most important ones is it allows for multiple inputs to be studied at once. So the traditional sensitivity analysis method is you keep everything the same while you vary one particular parameter, and then you see the effect of that parameter. That is fine, and that is useful in its own sense. But I like using Monte Carlo because it allows us to see the interactions between different elements of the model. So that means I can see what happens when I have a really rainy day and also bad settling. Like it allows you to sort of look at those more extreme events. It provides you not only a relationship between those variables, like I can see what the results were like on really rainy days, but also a probability of something happening. That's the one really nice idea, a nice element I like out of that. It is an excellent form of doing uncertainty analysis. It's sort of reasonably straightforward to apply and to understand, and it allows users to see sort of the potential impact of those variables that maybe you don't really have a nice way to sort of measure them directly, some sort of hypothetical growth rate or half saturation coefficient. You can run a bunch of simulations on it and then see what its effect is. Excuse me. So the cons, of course, are that you have to decide what you want the input distributions to be ahead of time. It's not really a con as much as a requirement. You'll have to make some assumptions or calculate some information ahead of time before you get going. And as I mentioned, it is computationally intensive. These are potentially thousands of runs. I've seen our users do as many as 50,000 runs for a Monte Carlo analysis with GPSX. So sometimes, especially if you're doing a dynamic one, this might be the kind of thing where you sort of set it up, at the end of your business day and go home and then come back in the morning and, let it run overnight to do all those runs. Okay, so what I'm going to do is I'm going to pass it over to Nick now, and Nick's going to talk about doing a steady state analysis where we are going to be varying both design type and operational type inputs to the model. And I'll pass it over to you, Nick.
All right, thanks, Spencer. So as Spencer said, I'm going to be doing a little bit of a steady state analysis using the Monte Carlo tool. And one of the nicest ways to do steady state Monte Carlo analysis in GPSX is to apply it to a design problem. So that's what this case study is mostly going to focus on, basically how we use Monte Carlo to learn more about our designs, to make our designs more robust. But before I get into that, first, I just want to talk very quickly about the design process and why accounting for uncertainty is so important. So in typical wastewater treatment plant design, as many of you know, we typically would use something like Metcalfe and Eddy equations or some other reference and put those into design spreadsheets. And basically just use those spreadsheets to calculate our tank volumes, our clarifier sizes, things of that nature. And this is obviously a pretty good method. It's been done this way for years and it works well. But like anything we do in engineering, there's many inherent assumptions in this method, and all those assumptions obviously lead to a bit of design uncertainty. So just to go over quickly some sources of uncertainty in wastewater applications. One of the big ones is obviously the long design horizon. So wastewater treatment facilities are designed to be used for many years, and obviously over that period of time, influent flow, quality, even the population in the area can change. New industries can pop up in the area that's going to change the type of wastewater, and especially now, even with climate change, that kind of throws another wrench into the whole trying to predict what's going to happen in the future in terms of the wastewater quality. Another thing which kind of already mentioned is the influent flowing characteristics, but in this sense, I mean it more on a day-to-day basis. There's a lot of variance, obviously, in influent quality. For example, if you took 3 TSS measurements from the same spot at the same time, they're almost certainly all going to have slightly different concentrations. So there is just inherent uncertainty in basically anything we measure. Thirdly, the biomass types and kinetics. So with design equations like this, typically we're making some pretty gross assumptions about biomass. We're simplifying down and basically only using a few biomass types with constant kinetic parameters, like Spencer mentioned. So for example, every heterotrophic bacteria becomes heterotrophic biomass and is assumed to have the exact same kinetic parameters, where obviously in reality, heterotrophs are a more diverse group of organisms, and not every single individual bacteria is going to grow in the exact same way. Finally, also aeration parameters is a big one. So like the alpha factor for aeration, or like a diffuser fouling parameter, all of these types of things can lead to uncertainty. All right, so in typical design, then the way that we account for all these sources of uncertainty is that we use safety factors. Just as a little bit of an aside, there was this new scientific report that just came out from the IWA, the report on uncertainty in wastewater treatment design and operation. And if you want to learn more about safety factors and about the current practices and kind of where the field is heading in the future, this is a good report to check out. But I guess I kind of want to move past safety factors and move past this report and talk a bit about if that's even possible. Can we move beyond these kind of safety factors, or at least become a little less reliant on them using simulation software like GPSX? All right, so how can GPSX improve design? Basically, there's the simple things, like we know GPSX has very detailed models, and obviously these are going to help increase the accuracy of our solutions. So we have a lot of unit processes, lots of state variables, and many biomass types. So we are able to get a bit more of a precise or more nuanced answer than just using a few biomass types or some spreadsheet design equations. We also have the ability to run dynamic simulations. This allows us to look at potential problem scenarios such as wet weather events, if there's going to be any maintenance downtime, things of that nature. And then we also have the tools. So the sensitivity analysis tool or the optimization tool. And these we can use to find ideal designs. So we can try to minimize the tank size or minimize an effluent parameter, minimize some cost or things of that nature. So GPSX can really make design a lot easier and more accurate, but it can still get better because we're still making a ton of assumptions when we're using GPSX. For example, I'm just showing the heterotrophic biomass kinetic menu here. And you can see we have a ton of kinetic parameters for heterotrophs. So there's a lot that's gone into this model. And it does typically do a very good job. But as we said before, biomass is diverse, and a constant value can't really account for the range of possibilities and the range of rates or half saturation coefficients that the individual members of the biomass population can have. And that's why it's really nice to have a tool that we can use to kind of quantify this uncertainty. That is where the GPSX Monte Carlo tool kind of comes in. We can use it to quantify the impact of some of the uncertain things that we know might vary a bit, or we just don't have that much information about when we're designing, and then increase our confidence in our final design. All right, so I think the best way to kind of illustrate the value of this is to just do a quick example. So on the right here, I just have a very simple GPSX layout image. It's just an activated sludge process where we're trying to have just nitrification and DOD removal. So yeah, it's just an influent goes to the primary, goes through the secondary treatment, just aeration tank, and then to the secondary into the effluent. So it's a pretty simple layout. All right, so for the purpose of this case study, I guess we can just imagine that I'm an engineer and I'm working on this design. So I've been given some design targets. I need to meets the TSS needs to be less than 10 milligrams per liter. The BOD needs to be less than 5.5 milligrams per liter. The ammonia needs to be less than 1. And then this operating and amortization cost, I want to keep below $270,000 a year. Just as an aside, this operating and amortization cost, it's pretty simplified. It's basically, I'm just using the operating cost calculation in GPSX and then amortizing the capital cost, which is a function of just the tank sizes, so the clarifier surface areas and the aeration tank volume. All right, so to actually meet these targets, I've been given some design handles. So this is the aeration tank volume, the secondary clarifier surface area, and the watts flow rate. So I'm going to try to be adjusting these to meet these targets and some assumptions. Obviously, I do still need to make some assumptions. So I'm assuming the influent flow is just 10 mLD. Airflow is going to be controlled with a PID controller. So we're always going to have a DO set point and a DO concentration of 2 in the aeration tanks, and the airflow is just going to be calculated for us by GPSX. And the ROS flow weight is just going to be 1 times the influent flow. Okay, so with all this information in hand, I used GPSX to actually produce the design alternative where I'm meeting all of these targets. So I got all the effluent quality to be below their targets by setting the aeration tank volume to 1,800 meters cubed, the secondary clarifier surface area to 650 meters squared, and the WAS flow rate to 220 meters cubed per day. So at this point, if I didn't have access to GPSX and the Monte Carlo tool, this is where I'd probably just slap on a few safety factors and call it a day. I talked to someone at WEFTEC this year who told me that they do exactly that. They actually set up their design layouts in GPSX. They modify the tank sizes and the clarifier sizes until they're just meeting the effluent criteria. And then they just multiply all the final sizes they get by 1.5 and use that in their final design. And that approach obviously works for them and can get you something, can get you an answer that's going to work. But effectively applying Monte Carlo to analyze the design is an even better method because it can just give you more insight. So that's what we're going to do now. So the first thing that we need to do, obviously, before we apply Monte Carlo, is we need to define and at least somewhat quantify what our uncertain inputs actually are. So obviously, many things are going to vary a little bit in a wastewater treatment plant and can be considered uncertain. But here I'm just going to stick to introducing uncertainty into 3 different parts of the plant. The first place is in the influent. We're going to have a normally distributed influent COD. So the mean is going to be 420, and there's going to be a standard deviation of 30. So for each simulation, the influent COD is going to be sampled from that distribution. Next, as we've talked about a few times already, the biomass kinetics and just things happening in the bioreactor. So in this case, I'm choosing to vary the AOB and NOB max growth rates using a log normal distribution. And we chose this distribution based on a paper by Cox from 2004, who showed that log normal distributions are a pretty reasonable choice for activated sludge kinetic parameters. And as well, in the bioreactor, we're going to be varying the aerator fouling constant just using a uniform distribution. So what this constant is basically allows us to quantify the effect of aerator fouling on oxygen transfer efficiency. So a value of 1 meaning that the aerators are perfectly clean, it's not having any detrimental effect on transferring oxygen, and a value of 0 meaning there's no oxygen transfer. So we're just allowing it to range between 0.8 and 1 to say that sometimes maybe the aerators will be a little dirty, but it's never going to get too bad, but we just want to add that little bit of uncertainty in there. And then finally, in the clarifier, since we're making this design, for example, for a plant that isn't even built yet, we don't really have any idea what the sludge SVI is going to be. I shouldn't say no idea because we do have this range here, because we know the typical range that activated sludge SVIs would fall into, so we can just use that and make a uniform distribution on that so we can get a better idea of the uncertainty in the effluent TSS concentration. All right, so we have our design example. We have some choices for a potential design alternative, and we have decided that where exactly we're going to be introducing the uncertainty. So now I can jump over to GPSX and get into the actual demo. All right. All right, so this is the layout that I was just showing on the slide there. As you can see, I have my design handles here set to the values that I had selected earlier. And you can see the concentrations here, the design target summary. So I am meeting all the targets as I was required to. So I'm just going to show you quickly how to actually set up a Monte Carlo simulation. So I'm going to go over to this input panel here, the Monte Carlo analysis panel, and you can see I've already got all my variables on this panel that I'm going to be varying. So if I click this gear icon, it actually brings up this menu, and in this menu is where you would actually set up all the distribution parameters and anything like the mins and maxes and the standard deviations for all these variables. So I have them all set up, but for example, if I click on the sludge volume index here, you can see that there's a whole bunch of options, and obviously we want to choose the Monte Carlo option in this case. If I click on this image right here, it brings up the distribution choice. So I'm going with the uniform for the SVI because I'm saying I don't really have much information. I don't know if SVI follows a normal distribution, so it's safer just to use a uniform distribution in that case. But I could also do normal or log normal if I'd like. And because I'm uniform, I don't need to enter a mean or a standard deviation into those boxes. I just set up the max and min here in the menu. Okay, so now that I have those input parameters set up, the next thing that I need to set up is our special Monte Carlo output graphs. So Spencer showed a couple of these already, but basically all you need to do is, it's just like any typical GPSX output graph. So you go over to the output variable menu, grab the variable from here and drag it onto the output panel. Then when you have the variable on the output panel, you go to output graph properties, and then the type is where you have to choose what type of graph you want to use. So the very last one is the Monte Carlo graph. You can see it has more parameters, more things to set up than a typical GPSX just XY plot. You can choose the number of bins that you're going to be showing in your probability distribution histogram. You can choose to set a target and choose what the value of that target will be. So in this case, the BOD5 effluent target is 5.5, so I'm choosing that I want it to be less than 5.5. I could also switch this to be a greater than sign, say if I was trying to have a target for biogas production or something of that nature. We can put on the cumulative probability line and also choose the scaling for the Y and X axes, as well as the range for the X axis over here. Okay, so now I have the graph set up. I have the Monte Carlo input variable set up. So the only other thing I really need to do is just go to the Analyze tab, as Spencer said, and select Analyze mode. Now, default, this Monte Carlo will usually be on steady state, but so you should remember to make sure that it is on the Monte Carlo mode before you run the simulations. All right, so Monte Carlo is set up, Analyze mode is on, so now I can actually run some simulations here. All right, you see it's going fairly quickly. I've actually only chosen to do 100 runs here so that we can kind of see how these bars move as the simulations go on. And you can see every single simulation, it's sampling a different value from all of these distributions. I'm going to jump back to the slides now because I've actually run an 1,000-run Monte Carlo simulation previously, just so that we can have a bit of nicer answers to look at, and those results are back on the slides. So let me go back there. All right, so first I just have a little reminder here of what the deterministic simulation gave us. And then here are the output histograms from the Monte Carlo simulation. So immediately you can see that none of the targets were met in every single simulation. So basically the probabilities of compliance were all less than 100%. So for the BOD, it was pretty good. We met the target 98% of the time. The TSS was 84%. The total cost was around 93%, and the ammonia was around 80%. So immediately we can we'd obviously noticed that the ammonia and the TSS concentrations were the targets that were the most out of spec. And this really, I think, shows the value of the Monte Carlo simulation. So rather than just applying a blanket safety factor to everything in the plant, we can now go back and redesign our system keeping in mind that we need more robust ammonia and TSS removal. So basically, Monte Carlo shows us where our design is lacking and thus where we need to focus our design improvements. So we can hopefully avoid over-designing because now we have insights into where the actual problems are or where the potential problems could be. All right, so lastly, I just wanted to show this figure that I thought was pretty cool from a similar design as to the one I showed you in the example. So to make this figure, I ran a bunch of Monte Carlo simulations at different secondary clarifier surface areas. So each dot on the figure here is basically represents one of those Monte Carlo simulations. And the green dots actually represent the surface areas where that particular target was met for the deterministic solution. So it's pretty interesting. I think it's a pretty good way of kind of pushing the message that I've been pushing this whole time already, which is that Monte Carlo is a really nice way of just allowing us to see how close our design is to limits and can save us from over and under designing. Because in this case, for example, there's one point here where the TSS target is met with the deterministic simulation. So if you didn't have access to the Monte Carlo tool, you would think you're in decent shape. Your TSS target is met. But with just a little bit of uncertainty introduced, it fails the actual target 50% of the time. So having a tool that actually quantifies that for us is very, very valuable. And just as an aside, if you do want to do something like this, a nice way to do it quickly is to use Python to automate GPSX to run the Monte Carlo over and over again. So you can contact us if this is something that you're interested in, and we can help set that up for you. All right, so that basically brings it to the end of my case study. So I'm going to hand it over to Jacob to talk about dynamic analysis with Monte Carlo.
All right, thanks, Nick. I'm going to share my screen now. All right, so yeah, as Nick mentioned, I'm going to focus on kind of our second case study of this webinar, which is focused more on a dynamic analysis rather than just focusing on steady state analysis. And as mentioned, we're going to be doing this using Python. And why are we using Python to kind of augment GPSX's built-in Monte Carlo functionality? Well, there's a variety of reasons why you want to use Python in GPSX. First, when talking about Monte Carlos, it allows you the ability to kind of generate probabilistic inputs at any point throughout a dynamic simulation. You're not just limited to setting those inputs at the very beginning of the simulation. You also have the ability to introduce things like custom probability distributions. Say if you want to add in a binomial distribution, for example, as in GPSX, you only have that normal, log normal, and uniform. Or even if you want to add in some additional performance criteria that may not be available. You have the ability to do things like define custom variables and control logic that may not be easy to implement in GPSX as is. And then probably the most important and useful feature of Python is really just its ability to automate a lot of tasks. So this can be things like the ability to automate comparisons of potential designs that you have, or even to do things like creating your custom reports or figures that Nick kind of mentioned. And all that said, this is using Python. So if you are interested in kind of recreating some of this stuff on your own, please reach out to us about getting the GPSX Pro Plus license set up for you. So what is the problem that we're actually interested in solving in this particular case study? Well, we're taking that very simple plant that Nick had previously shown, and we have a couple of modifications. And the most interesting part of this is actually that now, instead of just having that typical wastewater influent, we also have a rainwater influent object and a hauled waste or sludge truck object also on our plant design. And with having these additional things, there are various sources of uncertainty that may come into your plant that are a lot more dynamic focused as opposed to just something that you can see in steady state. Just to highlight some of those, for example, our hauled waste truck object. We have a lot of uncertainty around this of in our dynamic simulation, how many trucks are we going to actually have show up at our facility? What will the volume of those trucks be? when are they actually going to arrive, and when will we actually have the ability to unload them at the facility. Then around your rainwater object, you have the uncertainty around, is it actually going to rain on a given day? What is the intensity of that event going to be if it occurs? How long will it last? And what point throughout your day will that event actually occur? Then finally, from a bit more of a operational standpoint, you have the operational status of equipment in your facility, where when you're doing the more steady state analysis, usually you're kind of assuming that everything is operating as expected. But something like your clarifier, if you have 4 clarifiers, one of them may not be operating in a given simulation, and that's something that you can also simulate in a Monte Carlo as uncertainty. So let's step through those 3 objects that I just highlighted and look at how we can address some of this uncertainty in a dynamic simulation using Python. And the first thing we're going to look at is the hauled sludge delivery, where we're going to be looking at uncertainty surrounding the delivery schedule of the trucks and what volume they're actually delivering. And before we get into the actual Python implementation, there are a few assumptions that we made around this type of delivery that are important to keep in mind. First, we're going to say that we can only receive trucks at our facility between 6 a.m. and 8 p.m. And if you take a look at this figure, you can see at points throughout our simulation, it's set to a value of 0 consistently, and that falls in those outside of those regions. We're not receiving any new trucks. We're also going to say that we can only unload 1 truck at any given time, and that we'll be unloading at a constant flow rate. And then finally, one last major assumption is that all of these trucks are going to have the exact same effluent characterization. Obviously, this is a pretty big assumption, and if you want to add additional uncertainty to your analysis, you can definitely vary these assumptions in your own implementation. But with that, let's take a look at how we would actually do it using those assumptions. So the first thing that we're going to do is we're going to define a global variable, which we're going to call sludge trucks, which is just a queue variable in Python. It's a queue data structure using the built-in queue library that comes with Python. And what that is just essentially a first in, first out data structure, so that we have the ability to say that the first object that comes into our script, or in this case, the first truck, is the first one that's serviced before we then look at the next one. So now, taking a look at the actual custom functions that we've defined, we'll take a look at the hauled sludge function. And the very first thing that we do in this function is we make a call to another custom function called check if truck empty. And what this does is it passes along our sludge truck queue, and it just is the simple thing of looking to see first, is our queue empty? So are there no trucks currently in line? And if this is not true, so we do have trucks at the plant, we then take a look to see what is the departure time of that very first truck in line. If our current simulation time is greater than the departure time, we're just going to remove that truck from our queue so that we can now take a look at the next one, because that truck is going to be empty in the eyes of our simulation. All right, going back to our main function, the next thing that we do is we get our simulation time, so just what point throughout our simulation is it? And with that time, we take a look to see our constraint of saying we can only receive between 6 a.m. and 8 p.m. So we see if our simulation time corresponds to within these bounds. If it does, we can make a call to our create sludge truck custom function. Where what this is a function where we go into that and we need to define a delivery threshold. And we're going to define our delivery threshold depending on if we have any trucks currently in our queue. If we don't, we'll define it to be 85. Otherwise, we'll define it to be 95. And where this deviation comes from is that we're saying that if we have any trucks at our plant, it's a little bit less likely that we will have more trucks show up to the plant. So we're setting our threshold slightly higher if there are trucks currently in our queue. So once we have that threshold, now comes where we're actually going to be introducing our uncertainty to our our Python script. And that's going to be done using the Python random library, where we're going to generate a random integer between 0 and 100 and check to see if that random integer is greater than our defined delivery threshold, so either 85 or 95, depending on our queue. And if it's greater than that threshold, that's where we're going to now introduce a truck to our facility and add to our queue. So we go into this logic here and we define a little bit more of our uncertainty that we have surrounding these trucks. So we say, how long is it going to take to unload this truck, where that's going to be a random integer between 1 and 12, and then we'll just multiply it by 15 to make it equivalent to minutes. We define the departure time, and that's just the sum of that unloading time from when it can actually be accessed. We define a little bit of uncertainty around what the volume of this truck is going to be, and then just define a constant unloading rate that we're going to use for unloading this truck. Once we have all that, we create an object to represent the truck that's at our facility by just defining a dictionary that contains these characteristics. And with that dictionary, we then just add it onto our queue. So now it's going to be at the end of the line. Stepping back to our main function one more time, we have a final custom function call that is unload trucks, where we pass our queue to this. And what we do is we take a look to see if our queue is empty, then we set the flow rate that's coming into our facility from the truck equal to 0. Otherwise, we set it to that constant loading rate we've defined for the very first truck in the queue. So now this is something that will be represented in the actual GPSX simulation. Okay, with that, we'll now take a look at the second source of uncertainty that I mentioned, which is going to be rainfall. And we're going to be looking at rainfall uncertainty that's introduced from first, the actual occurrence of a rainfall event, and then secondly, what are the dynamics of that rainfall event? And a few assumptions we're going to make are that rain is less likely to occur if the previous day was rainy. So we're just going to decrease the likelihood of a rainfall event happening on a subsequent day by 15%. We're going to say that all of our rainfall events are going to be confined to a single day, so they can't pass over midnight. They'll all be contained within 24 hours. Then a final thing that we're going to assume is that we're going to have the maximum intensity happen in the middle of the rainfall event profile, and there'll be a constant ramp up and ramp down to that maximum intensity. And the rainfall events that we've defined are going to be 3 distinct intensities of rainfall. So we made a log normal distribution that's representative of a low intensity storm, a moderate intensity storm, and a high intensity storm. You can see the PDF and CDF curves of these log normal distributions below, as well as you can see what the mean and standard deviation we use to define these particular curves. So now looking into how we actually implement this in Python, we'll start by once again defining a global variable, where this time it's going to be a dictionary rather than a queue. And we'll step into our custom functionality, so this rainfall function. And the very first thing that we do is we just find out what day in our simulation it is. And like I said, we're making the assumption that we can only have a new rainfall event once per day, so we can't assess this multiple times throughout a day. So we're going to see if this day is currently a key in our rain events dictionary. If it's not, then we'll step into this create daily rain event function. Passing it in our rain events dictionary in the current day, we'll go into this function, where just like we saw with the trucks, we're going to use a dictionary to store the characteristics of the rain events. And then we have some logic, where what we're saying here is we have a logic that is assessed if the previous day was a dry day, and a piece of logic that's assessed if the previous day was a wet day. And all we're doing in this logic is defining what our thresholds are going to be for rain. And as you can see, these thresholds above are a little bit lower than these ones below. And that's just because, like we mentioned, we're going to make it a little bit less likely that you'll have a rainfall event following a day that had rain. And we have 3 thresholds this time, because the first one's going to correspond to a low intensity event threshold, the second one a moderate, and then the third is going to be a high intensity threshold. Then just like we saw in the trucks, we're going to use the random int function to introduce our uncertainty to our simulation. And we're going to check the low intensity threshold to see if we're going to have a rain event during that time period. And if we do have a uncertainty that's higher than that threshold, we'll step into our create rain profile function. So this is how we're going to be defining our actual rain event, just like we saw with the trucks. So we'll address some of the uncertainties surrounding what time is that event going to start, what will the duration of the event be, and then we'll just define a list that we're going to use to actually set the profile that we're going to follow through that rain event. So we'll assess the thresholds to see which intensity this rainfall event corresponds to, where we have one for low intensity, moderate, and high. And now we're using the log norm variate function of the Python random library rather than the randint to get that log normal distribution to pick a number from that distribution curve. And there's various ones available to you in this random library if you're interested in other distributions. So once we have that maximum value, we'll say that the midpoint of our profile is going to be equivalent to the maximum. And then we'll just define our equivalent ramp up and ramp down profiles into our rain profile dynamics. Okay, stepping back to this function, all we do is we add our characteristics of our rain profile to our rain event, and then we add our rain event to our rain events dictionary, just so that we have one for that specific day. Stepping back into our main function one more time, we have one more custom function call, which is going to be set rain intensity, where what this does is we provide our rain events in the current day, and we first set the rainfall to be equal to 0 so that we have that default when there is no rain occurring. We then check to see if our current simulation time is greater than the start time of a rain event. If it is, we get the current step throughout our rain profile and the duration of the event. We check to see if we're at a point in our event that hasn't exceeded the duration of the event. And if we aren't, we get what our rainfall value is going to be, and we just assign that to the GPSX rainfall intensity in the rainfall object. And then we'll just increment that count of where we are in the event. All right, so the final source of uncertainty that we're going to take a look at is around the operational status of things like the clarifiers, where we're going to say that our plant has 4 clarifiers where they are equivalent physically and they get the same flow distribution sent to each of them. So we can represent that as just a single object in GPSX, where we just do that by summing the overall surface area of the 4 independent clarifiers. And one major assumption that we're going to make when generating our uncertainty surrounding this object is we're going to say that we need to have at least 2 secondary clarifiers in operation at all times. And when we take one of these secondary clarifiers out of operation, all we do is we reduce the combined clarifier's surface area by the equivalent of one of those clarifiers that's taken out of service. So stepping into the Python implementation of this, we once again define a couple of global variables where we're saying what is the surface area of an individual tank, as well as the total number of secondary clarifiers that we have in our plant. We go into our custom set clarifier status function where we assign the number of active clarifiers, and then we loop through each of these clarifiers independently to independently assess if they are operational. So we have in our control logic, do we have at least 2 clarifiers in operation? Because that's an assumption that we're making. And then we take a look at this clarifier out of service function call, where all this is just our uncertainty being added, is another random integer where we say if it's greater than 97, then this clarifier is out of service. Otherwise, it's still in service. And then we just decrease the number of active clarifiers if we need to and set what the total surface area of the secondary clarifiers is in GPSX. Okay, now that we have those uncertainty driving functions defined, how do we actually run a simulation in GPSX using Python? Well, there's 4 functions that you need to use to drive every GPSX simulation with Python. And those are the start function, where this is going to be called exactly once at the very beginning of your GPSX simulation. In our particular case, we're just going to set the length of our simulation, and that's going to be set to 3 days. We'll call our clarifier status function, and we're only going to do that in the start to assess the operational status of our clarifiers. And then we'll set a constant value for our primary clarifier surface area and our aeration tank volume. Next, you have your sync function, where this will be called at every communication interval throughout your GPSX simulation. And what we're doing is we're just going to call our hauled sludge and rainfall functions to add that uncertainty throughout our simulation. And then finally, you have your EOR or end of run function call, where this is going to be called exactly once at the very end of your simulation. And in our particular case, we just have a generic collect outputs function, but you could add other functionality here. But we're going to collect our outputs just so we can do a little bit of data analysis on it at the end. And then the final function that you will need is you'll need to have a run sim call somewhere in your Python script, where this run sim call is what actually triggers your GPSX simulation using the previous 3 functions. And in Python, anytime this is encountered, you will run a GPSX simulation. All right, so what is the operational problem we're actually trying to solve? Well, we're just going to compare the performance of two distinct designs. First, we have our base design. So that's going to look at our plant if it has an aeration tank volume of 900 meters cubed. It has 4 secondary clarifiers and 4 primary clarifiers, which each have a surface area of 25 meters squared. We're just going to compare how that performs against an expansion design where we increase our aeration tank volume to 1,400 meters cubed, and we increase our surface areas to 40 meters squared. So like Nick mentioned, these simulations in Monte Carlo take actually a very long time to run, especially if you are trying to run a large number. So I prepared the results that we're going to take a look at for this particular case study. And it's important to keep in mind that when you run this, every one of your inputs is going to be randomly selected, so it won't be consistent between Monte Carlo analysis, and you may not know what will be selected. But if you run a significantly large number of simulations, you will ultimately get the same input distribution from that randomness. And just to take a look at what I mean, for example, with our 1,000 run simulations, the kind of distinct distribution that we saw for the number of trucks was a bit of a normal distribution. You can see the highest probability is between 16 and 18 trucks arriving at your facility. And the scatter plot on this shows what the average sludge volume is for that number of trucks. And as you kind of expect, it does show kind of a linear increase as more trucks arrive at the facility. Next, you can take a look at the distribution of the secondary clarifiers in service, where you can see most of the time we do have 4 secondary clarifiers in service, so almost 90% of the time. And then the remainder is either 3 or 2. And then finally, the distribution of the number of rain events, where you can see about 50% of the time we do have 1 rain event in that 3-day horizon, but a quarter of the time we have 0 or 2 events. So finally, we'll take a look at how these models performed. And first, taking a look at our solids, you can see that our TSS and COD didn't perform too great in our base case. But when we actually increased our sizing to our expanded case, you can see that this actually did result in a pretty significant reduction in the exceedance, where we're defining exceedance as percentage of the dynamic simulation that is above our target value that's specified there. So you can see that, as you would kind of expect, these solids removals are very highly related to the actual sizing of your plant. But then taking a look at the nitrogen variables, you can see that ammonia and TKN actually did perform relatively well, or pretty well, in our base case. So you aren't going to see much of a reduction from increasing the size of the equipment in your facility. And this is kind of expected, as these things are tied more closely to things like your SRT, where if we're already meeting that, just increasing the size won't help a lot with reducing that. And one final thing you can do when you run your analysis this way is you can take a comparison of your exceedance versus independent parts of your Monte Carlo analysis. Or for example, we're showing the TSS exceedance percentage versus the rainfall volume that entered the plant during that simulation. And our expanded case is shown in blue, while the base case is shown in orange. You can see that there is a shifting happening in that expanded case. This would be expected because as we increase those sizing, we do have a bit more resilience against those increased flow rates coming from the rain volume. So you can see that these the characteristics that we're changing are very correlated to this particular input. But then if you look at something like the truck volume, you can see that even though there is a slight decrease in that expanded case, it still gives a very similar output to what we saw in the base case. So it just shows that you need to keep in mind what you're actually looking at when you're doing this Monte Carlo analysis, and keep in mind that even though you are changing many variables, the things that you're seeing may not be very closely correlated to that, as we didn't need much more capacity at our plant to actually handle the truck volumes. All right, with that, I'm going to hand it back to Spencer to just give some concluding thoughts on our webinar.
Thank you, Jacob. So I have just a couple of final thoughts here. I wanted to mention the fact that, as we alluded to a couple of times, the GPSX Monte Carlo feature that we built in, and also the example of what Jacob was showing from Python as well, there's an inherent assumption built in there that the inputs, when we sample them, are uncorrelated, meaning that we sample from each of those individual distributions separately from each other. So that is fine for many applications. However, for something like an influent concentration, though, there may be situations where they would be correlated. So to give you a quick example, when I have high TSS, I probably have higher COD as well. So there are ways that we can implement that as part of there are techniques to be able to develop that relationship. I was going to originally include that in the webinar today, but when we discovered the length of this, we're almost up to an hour here, we decided to leave that out for now. And if you want to get more information on that, please just email us and I can sort of fill you in on what to do. Other thought is that basically there are endless different types of outputs that you can collect. Basically, even though you're only selecting a handful of inputs to apply your randomness to, you can collect all the GPSX output that you like. Every one of them will be, a function of whatever that simulation was. So that all of them could potentially have a distribution calculated for it, and then you could analyze that. So make sure that when you're doing this, you pick the outputs that you're really interested in, and look around, and maybe there's some stuff in the bioreactor, or maybe in the clarifier, and obviously in the effluent, that you want to be able to, after the fact, take a look at how they were changed over time as you generated all of that output. So put them all on graphs, let the system dump out all of that output, and then you can analyze them after the fact. But they do have to be either on a graph if you're using the first method, or if you're using the Python method, you have to explicitly export out that information. So in general, though, Monte Carlo, it requires some consideration about what inputs you are going to do, and what, apply the randomness to, and also, what those distributions are going to look like. But really, overall, it's a very useful tool, and a very sort of nice approach to being able to introduce maybe, an extra little, a more detailed level of analysis into your modeling work that you're going to be doing for your clients. So I know it's very popular with a certain handful of our clients that many of them have been using it for many years, and it's part of most of the applications that they do. And so we would be happy to help you implement that if you have any other further questions.